So we set our equation equal to standard form. Our goal is to solve it. So can we factor this? Annika. Good. So we can factor out 3x squared, and that's going to leave us with x squared minus 4x plus 7. Can we factor further the x squared minus 4x plus 7? No. Okay, so we could solve it other methods. So what we have here is we have a factor and another factor. This factor can't get factored any further, even though it's not like as simple as we would like it. So then we go to start solving by setting our factors equal to 0. So when we set the first factor equal to 0, yes, Molly, this is for you. So we set the first factor equal to 0. And we get 0 as a 0. What does that mean about the graph of our function? It passes through the origin. Okay? It has a 0 at 0 on the x-axis. What is the multiplicity of this 0? 2. Okay? Because it came from x squared, which really meant there was like 2 factors of x that each could have been set equal to 0, giving us 2 different numbers, but they're really the same number. So it's 1 0 at 0, but with a multiplicity of 2. So how do I expect my graph, if I did graph this function, to behave when it gets to 0? Will it cross right through? Annika?
It would act like a quadratic.
Good. It would act like a quadratic and hit and turn around right at that point, right? That would be our expectation. Okay? Now, this wasn't factorable, so I can't factor it to get the solutions. But what was pointed out to us is we could complete the square. We can use the quadratic formula because now this part is a quadratic. So when I'm solving just this factor, since it is quadratic itself, I can use anything that we learned in the last chapter, which was about solving quadratics, in order to solve it. So you can complete the square. You can use the quadratic formula, whatever you prefer. So it looks like this, and if we simplify this, okay, we get x is equal to 4 plus or minus the square root of, what? Oh, sorry. 16 minus 28, which is negative 12, all over 2. Okay, good. So we see the negative under here. We don't stop. They didn't limit us to real solutions. They just said solve. So we're going to write these solutions in their complex or imaginary way. So this is going to simplify to be 4 plus or minus. How does the square root of 12 normally simplify? Michaela? Thank you, Michaela. Okay, so 2 rad 3. And it did have a negative underneath there, so like Stephen pointed out, we would want to use I, okay, over 2. Can we simplify this further? Yes. Okay, not just because 4 is divisible by 2, but because each of these terms in the numerator have a common factor with the denominator. That's when I choose to simplify further. Otherwise, I'd have to separate them. So 2 plus or minus I rad 3. So how many distinct solutions do we have? 3 distinct solutions. 0, 2 plus I rad 3, 2 minus I rad 3. How many real solutions do we have? 1. What is the degree of this polynomial we were solving? 4. So what's the maximum amount of solutions we could have? 4 is the maximum amount of solutions. 3 is the maximum amount of turning points, right? Now, I only see 3 solutions up here. Why don't I see 4 if I could have 4? Annika?
Well, there are 4 solutions, but 0 is squared.
Good. This solution has a multiplicity of 2. So overall, if I look at all the imaginary solutions plus all the real solutions with their multiplicity, I should be able to see what my solutions are, right? So this is like 2 of the factors of my polynomial, or like 2 of the solutions because of its multiplicity, and here's the other 2 reaching that maximum of 4. So you know how before when we only worked with real numbers, okay, or we didn't talk about multiplicity, it was weird that it had degree 4 but only crossed through twice or something like that, right? But now we see why. Maybe there was imaginary solutions. Maybe one of those roots had a different multiplicity. Yeah, Anna.
Just for simplifying,
Uh-huh.
only simplify the denominator when both of the terms can be
Yes, unless you separate it into two separate fractions, like the 4 over 2 and the 2I rad 3 over 2. What we've had a lot of people doing is saying like, oh, 2 goes into 4, so that's 2, and then they don't do anything with this. They keep it right here and ignore that the denominator is part of that also. So I just want to make sure people understand that. So are we okay with the fact that we can find imaginary or complex solutions, and that relationship between how many there are, if we look at multiplicity plus all the real and imaginary zeros, we can kind of see the total amount of zeros adding up there. Okay. All right. So the next thing we're talking about are some factoring patterns. Okay. So you guys know a bunch of factoring patterns. One of your favorites, I'm sure. If you have a squared minus b squared, how does that factor? Marlon? Good. Okay. A plus b times a minus b, right? Like if you have x squared minus 4, it factors as x plus 2, x minus 2. Are we all on board with that? Okay. So what happens if we change the degree a little bit if there's cubes? Okay. Okay, close. All right, so if there's cubes, let's talk a little bit, first of all, why this works. To get from a squared all the way to b squared, think about how we write a polynomial in standard form. We go from highest degree down to lowest degree for each variable involved, right? So a here has what degree? 2. Then if we were writing it in standard form, there would be like a term that had a to the first power, and then a term where there were no more a's, okay? But then notice there's a b squared at the end, okay? In polynomials, when you end up with that, if you write it in standard form when there's 2, okay, the b squared is going to start at the 0 power and work its way up a power. So here there's no b's, okay? Some middle term would have b to the first power, and then the last term has b to the second power. So climbing or decreasing in powers, okay? Which means that middle term of the polynomial would have to have an a to the first power to get from the second power down to nothing, and a b to the first power to get from no powers up to the second. So it would be like an a and a b. And you can see that because you know that when we FOIL, we get terms with a times b here, right? But one of them's minus and one of them's plus. That way, even if they're written there, it's not really worth anything, and it's still a squared minus b squared, right? Okay, so let's take a minute and think about if I have cubes. So a has to work its way. Good. The second term is going to be a squared b because a has to go down a power, right, so that eventually there's no a's left. But b is going to have to work its way up from nothing all the way up to b to the third. So the next term here is going to lose a power of a but gain a power of b. Okay? And then the term after that is going to involve ab squared. Okay? But I'm going to be a little bit strategic about where I put them. I can't just put those in, right? Now I've changed it. It's not just a cubed, b cubed. I really need 2 of these and 2 of those, 1 minus and 1 plus, right? That way, they technically cancel each other out. Like if I go like this, those are there, but they're really worth nothing, right? Okay. Now, technically, you can write them in any order, but what I'm about to do requires that I have a certain order. Hopefully, I picked the right one, and if not, I'll have to rework it, okay? Now what I'm going to do is I'm going to factor this. So this is technically a cubed minus b cubed, right? I put a bunch of other stuff in here, but the other stuff I put in really cancels itself out and is worth nothing. Are we okay with that idea? It's just a really weird way to write it, okay? So now I'm going to go through, I'm going to factor. Now, there's nothing that they all have in common. I don't know off of the top of my head how to factor this. So what I'm going to do is I'm going to take a grouping approach. So do you guys remember that when nothing had, like every term didn't have something in common, you could take kind of a couple terms at a time and pull out what they had in common, hoping that once you finished, you saw some common stuff between them, okay? So if I look at the first 2 terms here, what do they have in common? And that would leave me with, okay. Then these next 2 terms, what do they have in common? AB. Told you guys I was strategic about the way I was ordering them, right? Hoping I worked it out right. And then these last 2 terms, b squared. All right. So I did choose a good order. Why do I think I chose a good order? They all have a minus b. So that means there are 3 terms that I see here right now. 1, 2, 3. And those 3 terms have a common factor, which is a minus b. If I factor a minus b out of the first term, okay, you know what? What's left in the first term? Just a squared. And if a minus b is distributed there, that would be that term, right? If a minus b is distributed to the second term, what would it have to be for us to get this second term? ab, and then b squared. This is the new pattern that we have to learn, okay? Because this is how a cubed minus b cubed factors. It's a weird pattern to learn. This is why it actually works, okay? Because this is the only way we can factor it through this grouping with all those things in the middle. So going back to writing down the actual patterns. Okay, so the difference of cubes is going to be when you have a perfect cube minus another perfect cube, okay? The sum of cubes is going to be when you have a perfect cube being added with another perfect cube. Now, the patterns have some distinct similarities. They're not that different except for the signs that accompany them. So we just did this one, okay, and it turned out to be a minus b was the common factor between all of those terms that I grouped. Then there was an a squared plus ab plus b squared. This one's a plus b, ends up being the common factor. It still ends up being a plus b squared at the end. Otherwise, you wouldn't be able to get plus b cubed, because the only thing that's going to make b cubed is that times that. But you got to get some stuff to cancel out, so you got to have a negative somewhere. So this has to be the negative here. All right, so we have to learn these 2 new factoring patterns. Okay. So what are some, as you guys are writing them down, okay, they're kind of structured similarly, just with different minuses and pluses. What are some patterns that you see? What are you immediately thinking in your head? Here's how I'm going to remember this. It kind of looks like this. It kind of goes like this. What do you see that's going to help you remember? Justin. Okay, good. So the first factor tends to match what's going on in the problem. So if it's a sum, the first factor is a sum. If it's a difference, then the factor is a difference. Okay. Any other patterns that you guys see that are helpful in holding on to? Karen? So the next sign is always opposite the one that you wrote down. So you can first write down a matching sign to the problem, and then the next sign is always going to be the opposite of that. Okay? So if it's a difference of cubes, I have a minus, and then I have a plus as the first one in this factor. Here, it would be a plus and then a minus. And what about the last sign?
It's always positive.
It's always positive. So Miss Harper has a fun little way to remember this. I'm not big on, fun ways to remember, so I just share with you other people's fun ways to remember, okay? So soap, okay? Same, opposite, always positive. All right? That is fun, huh? This is why I sometimes don't like those things. This is what I don't want you to ask me during a test. Ms. Dahl, I know it's soap. Can you just tell me? I forget what the AP part. I don't even get. What's the A, right? That's the question I get, and then that's why the little tricks bug me. But if it works for you, then it works for you. If it's working for you, you won't ask me. Now no one will probably ask me because I made a big deal about it, right? But, all right. So if that helps you, woohoo. If it doesn't, make a flashcard. I don't know, something, right? Okay. All right. So we have to know these factoring patterns. How these factoring patterns will help us. Does everybody have the 2 patterns down? So we can go use them now? All right. What are all the real or imaginary solutions of this equation? First, if I was to give you this problem when you had first walked in today, I feel like I could give you this problem as a math moment. I feel like you've probably solved something similar to this in Algebra 1. How would you approach solving this problem? Justin. Good. Okay. Good. So we divide both things by 2. We have x cubed equals negative 27. So it's basically asking you what number to the 3rd power equals negative 27. Okay. Which you either know is negative 3 or mathematically the operation you're doing is you're taking the cube root and you're getting x equals negative 3. Now, no imaginary number here. Why not imaginary? There's a negative inside a radical. Karen? Good. Okay? It's a cube root, not just a square root. Can you cube something and get a negative number? Yeah. Imaginaries came into play when there was issues with, like, when we square something in the real number system, we don't get a negative. Right? Okay. So there's not plus 3 somehow, but we are missing some solutions, and here's how I know. We might not be missing any real solutions, but we're missing something. This is a solution, a real solution. So on the graph, we expect this graph to cross through negative 3. But what shape is this graph? Yeah, it's a cubic, okay? So it's squiggles or whatever, right? Different end behaviors. But it should have up to how many zeros? 3. We only found one real one, which means either the rest are imaginary or this root is of multiplicity 3. Is this root of a multiplicity 3? We didn't do this by factoring, so we can't just look at the x cubed. Now, if it had said x cubed equals 0, that's x could equal 0, x could equal 0, x could equal 0, then there's a multiplicity of 3. Okay? But we didn't do this by factoring, right? Did we factor the polynomial? No, the 27's on the other side. Okay? So let's look at if we do it by factoring. Yes. So if we had done this problem by factoring, we would have brought everything. Oh, really? Apparently I'm taller than I thought. Okay, we would have brought everything to one side of the equation. And then we would have attempted to factor. Okay? How would we factor this? Max. Okay, 2 is the greatest common factor, and you could divide by 2. I'm running out of batteries. No, it's running out of batteries. All right. So we can divide both sides by 2, or we can factor out the 2. I'll write it as a factor this time to address some of those questions that arise. What about the x cubed plus 27 part? How does that factor? Molly? Okay, so there is going to be an x plus 3, but is it x plus 3 cubed? Because that means x plus 3 times x plus 3, which will give you like x squared plus 6x plus 9, times a whole nother x plus 3. That will give you an x cubed at the beginning and a 27 at the end, but it's going to give you a bunch of stuff in between, right? So this is why I know that this root does not have multiplicity 3, because one of the factors is not x plus 3 to the third power. Okay? What is special about x cubed and 27? They are both perfect cube roots. Therefore, what we are staring at when we're looking at x cubed plus 27 is a sum of cubes. So look at your pattern for your sum of cubes. Okay? We have x cubed plus 27. This means our first term is the perfect cube of x being cubed. Okay? 27 is the perfect cube acquired by cubing what number? 3. So our factors, or our a and our b, like we saw in our factoring problem, have to do with x and 3. You already have the first factor right here, x plus 3, a plus b, right? What comes in your second pattern, or your second factor in your factoring pattern? What should it look like? Annika? Good. Okay? According to the pattern. So here, can 2 be equal to 0? No, 2 is 2. There's no place for me to plug in x, whatever. So it is a factor, but it does not contribute to my solutions, okay, because it can't be changed, its value. This can contribute to my solutions because when x is equal to negative 3, this factor would be equal to 0. Now, this other factor, can it factor any further? No. So we could use the quadratic formula or completing the square in order to solve the quadratic factor. Okay? So if we go ahead and use quadratic formula, we will get 3 plus or minus, let's see, 9 minus 36, negative 27. Take a little space over here, sorry. So my final answer for those solutions will look like 3 plus or minus. What does rad 27 break down to be? 3 rad 3 and then with the I for the negative. Okay, so So yes, -3 is a solution, and it is the only real solution. But if you are looking for all the solutions of this polynomial, you would have to go find the imaginary or complex solutions, which would require you to know this factoring pattern and be able to come up with that quadratic. Okay? And what that tells me about this cubic, if I graph it, is like we talked about, this root is not of multiplicity 3. So it's not like it just passes through -3 all fancy like a cubic. Okay? Instead, what this tells me is it passes through -3 like normal, and then it probably turns around somewhere else and keeps going, but none of those places where it turns around dip back down far enough to go through the x-axis and have a real 0, which is why instead I have imaginary zeros. Because remember when, like quadratics, right, if they were up here above the axis, we didn't have any real zeros, but we had imaginary zeros. Okay, so we can see that relationship there. Okay? All right, so are we okay with solving that? We're using a bunch of our quadratic stuff, but there's one new factoring pattern we have to learn sometimes to see the quadratic within a cubic. Okay? All right, I'm going to come back to the calculator part. I'm going to let you guys end on that. Plus, we've already done all the calculator stuff with quadratics, so it's more like review. So, example 4. What are 3 consecutive even integers whose product is 4 times their sum? Okay? So first, I want you guys to try this in your groups. Okay, so one way is to make an equation, graph it, and then see where the solutions are. Okay? What was your equation?
I did 4x. Oh, I did 4 and then times x.
Okay, 4 times x.
Plus x plus 2 and then plus x plus 4, which is 3x plus 6.
Okay, so let's talk about where he got this from first, okay? This is 4 times a sum. Notice in the problem it says 4 times their sum. So he didn't just make up a sum. This is the sum of what's supposed to be the 3 numbers. Why is he representing them as x, x plus 2, and x plus 4? Janae?
When you take the first number and add 2, then it's also the same number, and then when you add 4, it's also the same.
Good. So consecutive integers, you would start with 1, you'd add 1, then you'd add another. Even integers, you need to skip 1 in between, so x, x plus 2, x plus 4. Okay? Funny, because it would look the same for consecutive odd integers, x, x plus 2, x plus 4. Okay? But you just have to look at solutions that start with an odd number instead of starting with an even number. Now, he said he set up an equation, so what did you set it equal to, Marlon?
I set it up to x. I got x times x plus 2 times x plus 4.
Good.
And then I got...
And out of your electric game.
Then I got kind of lazy at this point. I just like
Uh-huh.
X'd out the whole side on the left and then minus 4 3x plus 6 on the right.
Okay. I'm going to do it the longer way for the people that aren't.
Equals y.
Okay. All right. So what he did is he essentially brought everything to one side, so he had an equation that's like y equals all of this stuff because he used it to graph and find when it's equal to 0. So essentially on this side, all of this stuff adds up to be 3x plus 6, and that's supposed to be multiplied by 4, so this is going to be 12x plus 24. And on this other side, x plus 2 times x plus 4 would be x squared plus 6x plus 8. And all of that multiplied by x would be x to the third plus 6x squared plus 8x. And then I want to set everything equal to 0, or in other words, how he did it for his equation was having y equals. So this would be x cubed plus 6x squared minus 4x minus 24. Okay? So he then put it in the calculator as y equals this equation, and then found where the zeros were. Okay? How could we do that without a calculator? Say we didn't have the technology. Perfectly good plan. I didn't limit you guys. Perfectly acceptable. What would we do if we didn't have a calculator? Justin. Now, the difference or sum of cubes would work, but it only works if you just have 2 terms, right? And both of them are perfect cubes. So this has a lot more terms than 2.
Oh, we can group factor.
Good. We could group factor in. So here, the greatest common factor is x squared, and that would leave us with x plus 6. And then here, I detected it before they did. Okay, so here we could take out -4 and leave us with x plus 6, okay, which would give us that 0 is equal to x squared minus 4 times x plus 6, or x minus 2 times x plus 2 times x plus 6, giving us 3 solutions: 2, -2, -6. What are these 3 solutions, though? Because they don't look consecutive, right? Max? Good. So we only solved for x. Remember that x represented for us the first number in our consecutive list of numbers. This is why people were able to come up with 3 different solutions to that problem, because one solution would start with 2, and the next even integer after that would be 4, and then 6. So that's one possibility. Okay? Whereas the next set would start with -2 as the first number option, which would then have 0 and then 2. And then the last option would say start with -6, which would then have -4 and then -2. Okay? Is this all right with everybody? Yes? Okay. So going back to the calculator, okay? Somebody tell me, without getting out your calculator yet, I'll let you guys check and see if you can do it in a minute. But if you got a problem that said, use a graphing calculator to obtain a complete graph, find each real 0 to the nearest hundredth, and state the relative maximums and minimums, what tools are you using on the calculator? Okay, the graphing tools. So you're going to go to y equals, you're going to put in your equation, you're going to graph. Is your window going to fit perfect every time the first try? No. You have to be smart enough to fix your window to the areas you need to see. So let's say you fix it all, you get the pretty little picture in your window. How are you going to go find the zeros? Molly? Good. So second, trace, which really gives us the calculate menu, and we would choose the choice that says zeros. Okay, and it's going to ask you for a left bound and your right bound. Remember, if you're looking at a graph that's crossing the x-axis, if there's 3 zeros, you're going to have to do 3 different calculations. If you are trying to calculate this 0 right here, your left bound is over here on this side, okay? Because I know that's below, but if you want to be on the graph but to the left of this point, the only way to get there is to travel along the graph this way, which is going to the left, which happens to be below. And the right bound, so this would be our left bound, our right bound would be up here, okay? However, if we were trying to calculate this 0, okay, our left bound would be over here, and our right bound would be over here, because as we travel along the graph, below is to the left of the 0, whereas above moves to the right of the 0. Okay? So making sure you're doing that correctly. And then we went over yesterday, and while we did quadratics, how to find maximums and minimums. And again, this time, because they are of odd degree, there would be relative maximums and minimums, because they have end behavior in both directions, which means you have no true maximum and no true minimum. Okay? Does that make sense? Do you guys feel like you could go find those on the calculator right now? Yes? Okay, so go ahead and do that.